Hello, everybody. In Module 4, I discuss communication games between the managers and the market. Module 4 has 6 lessons. Today, we're focused on Lesson 4, Cheap Talk Models. In the previous lessons, we assumed that even though managers can strategically withhold information, any disclosure from the manager has to be truthful. One can think about this as a setting where the lying cost is infinitely large for the manager. Such assumption might be valid for certain disclosures, for example, 8K disclosures, but it's not valid for other types of disclosures, for example, management earnings forecasts due to safe harbor provision. In this lesson, we're going to focus on another extreme case, when the lying costs are zero. That's why we call this type of models cheap talk models. Talk is cheap because lying costs are zero. The discussions are based on Crawford and Sobel 1982 Econometrica paper, which is the first and a classical study of cheap talk models. Let's look at the setup of the model. There is a sender who is informed. Think about the sender as a manager. The sender observes a piece of information M, and the sender sends a message N to a receiver. Think about a receiver as a shareholder or shareholders of the firm. Because talk is cheap, N can be anything. N is not necessarily equal to M. The receiver then takes an action, Y, that affects both the sender and the receiver's payoffs. We're going to see an example of Y in the shareholder manager setting very soon. Assume that M is uniformly distributed on 0 and 1. Without loss of generality, we also assume that the message is also in the same interval, 0 and 1. The sender's payoff is a quadratic loss function, with loss minimized at M plus B. And the receiver's payoff is also a quadratic loss function, with loss minimized at M. B represents the conflict of interest between the sender and the receiver. The larger B is, the larger the conflict of interest between the sender and the receiver. In Lesson 1, we say that if there is no conflict of interest between the sender and the receiver, say B equals 0 in this case, then the sender is going to send a message M. M would equal to M, and there is no interesting disclosure issues to study. It motivates the payoff functions, and to give an example of Y, think about Y as the amount of investment in a shareholder manager example, and M as the fundamental of the firm. In this case, the receiver or shareholders wants to match the amount of investment to the fundamentals. They don't want to overinvest or underinvest. But the sender, as the manager, wants to invest more due to, for example, private benefit or empire building preferences. Another example could be that the receiver is the CEO of the firm who wants to invest based on the firm's fundamentals. The sender is a regional manager who wants more investment for his or her region. This is just a special example of Crawford and Sobel. Their original paper have more general preferences and more general distribution. So if you want more details, check about the paper. To solve for the model, first know that even though the actions that can be possibly taken in equilibrium is continuous, in equilibrium, the actual set of actions taken is finite. This means the conflict of interest between the sender and receiver, as well as the zero lying cost, results in equilibrium actions cannot be arbitrarily close to each other. The slides provide the illustrative proof. I'm not going to go through the proof in detail. I just want to give you a big picture intuition. The big picture intuition comes from the conflict of interest. Because the sender and the receiver, their preferred action for the same M has to differ by B, which means that any actions taken in equilibrium that are acceptable to both the sender and the receiver has to be differ by at least a B. Because your total action space is between 0 and 1 is 1. That means the total number of actions in equilibrium has to be at most 1 over B. And the implication of this result is that, in general, the actions taken will be an increasing step function because the equilibrium action has to have a finite number. So it cannot be a continuously increasing function. So for finite equilibrium actions, the only possibility is a step function. It's increasing because when N is larger, it's more likely M is larger. So you take higher actions. And all equilibrium are partitioned equilibrium, which means that you partition the 0, 1 action space into a set of intervals. And then the message will indicate that the sender has the information that M lies in one of those intervals. And so sender with M belongs to one of the intervals, they're going to send a message that my M is in this interval. And the receiver, of course, is going to choose action based on this information. The receiver knows that M lies in the interval between AI and AI plus 1. And because M is uniformly distributed, so the receiver's action is going to be the expected value of M, conditional M, lying between AI and AI plus 1, which is AI plus 1 divided by 2. The interval endpoints, other than the first one, they're not arbitrarily chosen. At those endpoints, the sender observing M equals AI can send a signal, either indicating that M lies in the interval between AI and AI plus 1, or M lies in the previous interval, the interval between AI minus 1 and AI. At the endpoints, they have to be indifferent, which means that their payoff functions from sending those two messages has to generate the same payoff for the sender. And this indifferent condition generates a recursive equation between the different interval endpoints. And one can prove, based on those recursive equations, by mathematical induction, that those equations has a class of solutions of the following form. You can see A1 is arbitrarily chosen, but once A1 is chosen, all the interval endpoints are chosen. In addition, even though A1 can be arbitrarily chosen, can be arbitrarily close to 0, all AIs has to be smaller than or equal to 1. That means you cannot increase the number of intervals to infinity. There is a maximum number of partition points such that at the last partition point, AI has to be still smaller than or equal to 1. And this defines the maximum number of partition. And this number of partition has to satisfy that 2i times I minus 1 times b is smaller than or equal than 1. And we can show that the maximum number of partition intervals has to decrease in b. So lower b would have higher number of partitions, and so more informative disclosure. Because you have more intervals, each interval is finer. When b is sufficiently large, in this example, when b is bigger than or equal to 1/4, the maximum number of partitions is 1, which means completely uninformed disclosure. Because that means regardless of what sender observes about M, the sender is going to send a message that M lies between 0 and 1. And the receiver already knows about that. This result is very intuitive. Less conflict of interest results in more informative disclosure. If the conflict of interest is sufficiently large, there can be no informative disclosure. We can also show that the receiver and sender's ex ante utility is increasing in N, which means that both receiver and sender, they prefer equilibrium with more partition. This is also intuitive because equilibrium with more partition, they convey more information about M. And this information is going to benefit both the receiver and the sender ex ante. Before I know about anything about M, I still prefer more information about M. Talking about accounting applications of cheap talk models. Gigler 1994 JAR paper is one of the applications. It studies a setting when the manager wants to disclose good news to investors, but the manager wants to disclose bad news to competitors. The manager wants to tell investors the firm is doing good, but wants to tell bad news to competitors, the firm is doing bad. Do not enter the market. So this conflict of interest is going to generate interval disclosures. And this paper is also interesting in another perspective. It may be useful to think about interval management earnings forecasts using the motivation of this paper, because the theory predicts that the interval is going to be larger, the conflict of interest is larger. So then this might be a testable empirical implications. And Morgan and Stoken in 2003, a RAND paper, they exploit this discrete nature of strategic communication in cheap talk games to study analyst recommendations. And in their setting, there is a mixed game of truthful communication when analyst incentives are aligned with investors, and cheap talk, which is when analyst incentives are not aligned with investors. And investors are not sure whether analyst incentives are aligned or not. And they find that even with some probability, some small probability that analyst incentives are not aligned, cheap talk equilibrium would dominate, and it results in partitioning equilibrium. And they also offer some new insight. Considering the analyst incentives may be aligned, that results in credible communication of bad news, but not credible communication of good news. And this is something that Crawford and Sobel did not establish. To conclude, when there is incentive conflict between the informed sender and the uninformed receiver, if lying is costless, then full disclosure is impossible. The question is whether or not we can convey any information. If the conflict of interest is not too large, some information can still be communicated, but the information communicated will be in the form of discrete intervals, those partitioning equilibria. In the next lesson, we're going to relax the assumption that lying cost is zero. So lying cost would neither be zero nor infinite. If you want to test your understanding of this lesson, check the review quiz at the link provided in the slides. Thank you very much.